But I don't see you yet, but in 1 second.
Same thing. Oh, we don't see a picture.
I lost my assistant here who is handling the console. 1 second, let me see.
Maybe it's because of...
We cannot see you too.
1 second, do not panic.
We're not trying.
Ναι, όχι, την κλείσανε για να πάνε σε μία γραμμή. Το ξεπάτησα, ναι. How is that now? Can you see me?
No.
No, well. Τι κάναμε τώρα?
Δεν ξέρω. Πατήσα...
Εγώ δεν πάτησα τίποτα, μόνο το mute πάτησα.
Μισό λεπτό. It called, there was no ring. I thought you fixed it when you... Yeah, I did.
You have the same phone?
Well, anyway, I can hear you loud and clear. So now that you are waiting to see me and I'm waiting to see you.
We have a minute now or not yet?
Έλα, ξαναξεκινάνε. Ξεκινάνε, θα ξαναβάλουν, τώρα θα ξανατηλεφωνήσουν.
Περίεργο πάντως. Να ελέγξω λίγο αυτοί μας
ναι,
σβήνουν.
Εντάξει, πρέπει να σβήνουν.
Λέει αυτό το permanent. Αυτό
όλοι είναι permanent. Γράψτε εδώ λίγο στη γωνία και σβήστε. Όχι, έσβησε. Okay, I can see you now. Καλά, δεν το χρησιμοποιήσω μαζί. Δεν θα χρησιμοποιήσω τους άλλους. Τώρα με κάτσε. Ναι, είναι με ένα κανάλι. Okay, oops, expired subscription.
Oh, like it's starting. He's yelling.
Okay, can you hear me now?
Yeah.
I can see you and I can hear you.
Veseli казали, че сме на два канала. Нали не сме на един. Пак сме на два.
Now it's two?
Yes, two channels.
These two channels now? Or one channel?
It's two channels, but we see you even clearer. So.
Okay, no problem. But I can see you very well. This is beautiful. I can see you even better than before. So we have to play with it. Okay. I'm sorry, guys. There is no easier way that I can try to tell you, convey to you what we have to learn. And if you watch it a little bit, we are going to come out okay. If not, send me your questions. I'll answer them. I mean, I said that email is for you to use. You don't use it. I keep insisting of getting an email once in a while, and then I get nothing for a big silence. So, don't make me make the course difficult so you can send me emails.
That's okay. We understand it now.
Okay. So, now if we go to the heart itself, it means that many cells will have many little vectors representing them, correct? Each cell, one vector, for each time instant.
Each what?
Each cell is represented by one vector at each time instance. So, at any moment, the heart looks like electrically speaking, the heart looks like a whole bunch of vectors. Electrically speaking, okay? So, if you recall the slide that I had put on before about how you add vectors, you get something like this. I mean, I took a few vectors that I had in the previous slide, and I moved them all parallel to their original position, and they all add up to something like that red vector there. This is the addition of all the small vectors. Now, because you have direction, some vectors cancel each other, and at the end you have one vector that represents everything. at each time instant. That is called the instantaneous heart axis, or axis of the heart.
The instantaneous? What?
Axis, the instantaneous electrical axis of the heart.
Okay.
Okay?
Electrical axis.
And what's that?
What it is at every moment there is one vector that represents all the electrical activity of all the cells in the heart at that moment.
Okay.
Between the electrodes.
What's that? That's not between electrodes. This is the actual vector that represents the activity of the heart.
Of the whole heart.
Of the whole heart. So the question now becomes, how do we go about measuring that vector? Okay? And we do that by putting electrodes in 3 places. Your left arm, your right arm, and your left foot. Now, your right foot is free. So what we do there, we put an electrode and we connect it to the ground. So we have your body grounded. So even if we give you a jolt by mistake, you don't die. Well, actually, there is another reason we do this. Those of you that are engineers should know that this way we make a fake baseline. But this is a different story. Okay? I think this diagram describes exactly what we do. Okay? One electrode you have on your left hand, an electrode on your right hand, an electrode on your left foot, and these 3 of them, if you look at them as the picture shows it, okay, they are pretty much equidistant. That is, they represent an equilateral triangle. Now, this is a concept that one night at the end of the 19th century, it dawned on the head of somebody by the name Eindhoven. And this is called the Triangle of Eindhoven. Eindhoven was a physicist, chemist, medical doctor, and a few other things all in one. And he is the guy that described the electrocardiogram first and foremost. We are still using his derivations, as they are called, the place that is where we put the electrodes to measure it, the same way as he did 100 years ago. Or whatever it is. I mean, I don't know if it's 100 or 98 or something like that, but it is a long time ago, before my father was born. Anyway, now why we do this, I will put it on the board to show you, so that we can. Okay, so what you have here, you have a description of this triangle that you saw in the previous picture, okay? And what you see there, you see some letters. On one side it says VL, on the other side it says VR, and down below it says VF, okay? Now, Eindhoven's idea was that you can represent the body with an equilateral triangle because electrically he measured resistances really, and he found out that electrically the resistance between your right and your left hand, the right hand and your foot, or the left hand and the foot, are about the same. Therefore, he figured that now he had a way that if he could fix the heart in the middle of the body, he could describe it. This is why he invented this system. What he described, you are going to see in a second. Okay? Are we together up to now?
Yes.
Yes. Okay. Now, why the left foot or the right foot? Does it make any difference? The answer is it doesn't make a damn difference. We use it this way because of convention and because we need one foot for ground. Okay? We could very well have tried to do it on a square or some other form of representation. Doesn't matter. This representation, though, of the equilateral triangle happens to be convenient. This is why we use it. And why do we use it? Because if you consider the heart to be in the center of this triangle, where the lines meet, okay, then you can project it on the sides and have the relationship that holds that I have written down below. 1 minus 2 Latin plus 3 Latin equals 0. What does that mean? It means that the projection of the heart axis, of the heart electrical vector, on the electrodes that join your right hand and your left hand, okay? Can you see it there? This projection is equal to what you are going to measure if you put a voltmeter between your two hands. I will try to draw it for a minute for you. All right.
You don't see the line.
You don't see the line, you'll see it in a minute. That's good you're telling me. Let me try with some other color. Now?
Yeah.
Yes.
This is the triangle, okay? What we have here, this side, my left hand. The other side, my right hand. And down here, my foot. Okay? In the middle is my heart. So consider this like this. One electrode here, one electrode here, and we take a wire, we go through a meter, and we come to the other side. Do you see this? Can you see it at all?
Vaguely.
Vaguely?
Okay, but,
Yeah.
but we get the idea, yeah.
We
You
get
get
it.
it?
We have the projection up.
So if you put between my two hands, you just put a meter to measure what is happening, you're going to measure basically the way the heart influences one hand versus the way it influences the other hand. And this is really the first, number one, bipolar measurement that you have of the electrocardiogram. In other words, as the axis of the heart moves here instantaneously, correct? My heart is pumping, right? Every time it does a circle, this vector that I said of all the cells keeps moving like this, okay? And as it moves, at every instant, you project it up here, and this projection is what you measure with these electrodes. So what you're going to measure here is you're going to measure some voltage. And this voltage is nothing else than the potential difference from one hand to the other, which represents what the heart is doing at that exact moment. You're lost, aren't you?
I'm not. It's okay.
What's good?
You don't understand me? Yeah?
So,
Okay.
no, really, if you're lost, please stop and let's go through this. These are not easy things. What I'm saying is that if you go and get yourself a voltmeter that's very, very precise and accurate and very sensitive, and you grab it between your two hands, you're going to see the needle of that going up and down, depending on what the heart is doing, what your heart is doing. Is that understood?
Yes.
Okay. Now, the reason we talked about vectors is because you need to understand them in order to make sense of what it means. Okay? And what you have to understand is that as the vector of your heart is changing in time, in other words, as in the middle of this triangle, the vector of your heart is changing with time, this is going to be reflected on what you measure between the two sides, between the two ends, the 2 points of the equilateral triangle that you have here. It is a mathematical, what you see here is a mathematical description of the actual phenomenon. So, if you have your heart here, and it has a vector that at one point looks like this, then as the wave of depolarization goes onto the heart, in another instant this may look like this, in a third instant it may look like this, in a fourth instant like this, then it moves and it goes through many, many cycles. Every time it repeats this type of thing because basically the cells in your heart are always depolarized in the same manner. Remember when we said this morning about the pathway that activates the heart? As long as that pathway works always the same way, the heart is going to be activated the same way. The vector is going to do the same typical round, and up here you're going to measure these things, many projections, which look like what we call a QRS. Each point on this curve is nothing else but one instant here, let's say instant 1, instant 2, instant 3. Then you can go here and say this is instant 1, and down next here is instant 2, and over here is instant 3, and up here is instant 4, and so on and so forth. You understand what I'm trying to say now?
Yeah.
That what you measure is nothing else but a representation of the projection of this vector on this side of the triangle. And this side of the triangle is nothing more than the measurement of one hand versus the other. Unfortunately, we have to play with dipoles a lot to understand these things. But once you do, what?
What's the peak? What's the height peak? Is that the net vector?
Each point is the net vector. Each point is.
The Q is the R and the S there. The peak is probably one furthest away because it's being measured this way. The peak is furthest.
Yeah.
This peak, you mean? Up
Yeah,
here?
that's right. Yeah.
Okay. This is the point where you have the depolarization of the ventricles. We're going to say what these things represent in 1 minute.
Okay.
We're going to say in 1 minute what these things represent. But what I want you to understand right now, that it is nothing else than a representation of what your heart is doing at every instant. As you measure that representation between your right hand and your left hand. Okay? Now, in order to always have the same readings, so that we can compare them, we have decided many, many years ago to put the electrodes in certain way, so that you have over here positive, over here negative. So when you measure these two things, this axis, your left hand is positive, your right hand is negative, and this is called the Latin 1, or the first bipolar recording. Okay? When you decide to measure between your right hand and your left foot, okay? By the way, over here I have written on the other, yeah. Over here you see a VL. It means voltage at the left hand. That's where the V comes and the L comes. On the other side you see VR, which means voltage at the right hand. So if you take one versus the other, you have the potential difference between the two hands, which potential difference reflects what the heart is sending to these 2 points in terms of currents. Okay? And when you see VF, it means voltage at the foot. So, the convention about it is that you have the first electrode is positive on your left hand, negative on your right hand. And when you measure your right hand versus your left foot, it is negative here, positive down here. And when you measure your left hand versus your left foot, it is positive at your foot and negative at your hand. This is a convention, nothing else. But it allows us to come up with a rule that you see on the right side. The first minus this, which is number 2, plus the number 3 equals to 0. So in effect, if you measure this difference and this difference, you can always infer what this one is. In fact, all the machines that measure the electrocardiogram today, one of the 3 they make out virtually. They don't measure all 3. They measure 2 and they deduce the 3rd from that equation. Okay?
Can you repeat what you just said about measuring 2 and then?
I said, you see down at the bottom it says 1 Latin minus 2 Latin plus 3 Latin equals 0, correct?
Yep.
Okay, what it means is that if you measure in 1 instant, let's say 15 seconds from the moment you press the button, doesn't matter, whatever, the difference, the potential difference between your left hand minus your right hand. And from that difference, you subtract the difference between your left foot minus your right hand. And you add to this the difference between your left foot minus your right hand, the total will be 0. This is what 1, 2, and 3 means. You want to start again?
Yeah.
Yeah, okay. Back to this little man here, or woman, whatever you like. We put one electrode on the left-hand side, one electrode on the right-hand side, okay? We connect them through an instrument to read. What are we going to see? We are going to see a potential difference, which is going to be changing in time. Why is it changing in time? Because our heart in the middle here is active. As the activity changes, this potential difference is going to change. You don't get it? Okay. Let's go back again. You understand why? How did we make the measurements in the case that we were doing single cell recordings? You remember? Let's forget all this. Let's go back to the single cell recordings a few days ago. Do you recall what we did? We took one electrode, we stuck it inside the cell, and we took another electrode and we put it on the outside, correct? You remember that thing that we had drawn? You can see here. We had one cell, and we said we put one electrode here and one electrode on the outside. I had drawn this thing on the board, if you recall. You recall this?
Yeah.
About cells? And then we said that as this thing, when this thing becomes active, this thing moves up and down. And this movement, if you record it in time, it gives you, for example, an action potential. Okay? You remember that?
Yeah.
Okay. And then we went on to say that this is what happens if you count one versus the other, the two electrodes, okay? But you could also put two electrodes here and measure the difference from here to here as current goes around. Yes or no? You remember that? You don't remember it here. You remember it here when we had the nerve action and we said if we put one electrode here, it will have a difference between the 2 points depending on where the action potential is.
Yeah.
You recall that?
Yeah.
Okay. Consider now that you have, instead of an action, you have the whole heart. The activity of the whole heart, would it or not be like the activity of many, many actions? It's going its own way. Yes or no? Right or wrong? Right. Okay. So we put one electrode in one hand, one electrode in the other hand. What are we going to measure? The potential difference between these two things, which is going to be big if the vector here that we're talking about, that is the total, the summation of all this activity is large, or small if the summation of this activity is small. Guys, I have lost you. Let's take 5 and get back to it. I'll figure something out. I don't want to lose you on this. It's very nice to... What?
sometimes can't hear you very well.
You cannot
It
hear
gets
me
fuzzy
very well.
when-
Can you hear me better now? Can you hear me better now?
Yeah. Now
Okay.
it's better, yes.
All right. Now we are going to do something about it next time, but let's take 2 minutes break so that I can refigure here how I'm going to present this to you, because I really want you to understand that. It's difficult, I understand, but no matter what you're going to take in front of you, it is going to be the same. So, what was this?
I understand the potential difference, which is the simplest one.
The potential difference.
Between, you put an electrode here,
Mm-hmm.
like a needle.
Mm-hmm. Yeah.
The vaccine.
On the left and right.
You put one here, and
Βγάλε
one
με
here.
Ναι.
Difference
Όχι, δεν πάγωσε η
between
εικόνα.
hand.
Ανεπάγωσε η εικόνα τους.
And all the potential difference is mainly the heart. What's the heart producing? The heart produces quite a big signal of electricity current.
Mm-hmm. So that's the you measure it.
That's the
So what was
ECG.
this
That's
one
the summation
minus-
vector.
Guys,
I didn't understand that.
can you tell your technician to restart this, because I have lost you. You're frozen.
Oh, you're frozen?
Yes.
I'll
Okay.
call him.
Oh my god. Oh.
Who is screaming like this?
I'm stretching, George.
What?
Stretch. I'm stretching.
Ah, you're lucky.
You're all like dressed up with a tie, and you have your mafia, some gun here too.
We don't have mafia here. This is a Bulgarian invention.
The
No,
mafia is getting bad.
Well, no, it was much worse. Now it's getting okay. Just stay away from them. They are, they are not the kind of mafia you have in the States, thank God. They are worse.
No, but the mafia is getting bad in Italy.
In Italy, forget it. Italy has gotten rid of them.
It's getting crazy there.
In Italy?
Yeah, they're just like the other day they shot at like so many people on the street.
When?
Last week I was hearing and the government is not doing enough.
Really? Because I thought that they had finished with them. Maybe not. I don't know.
No, they're getting back because they're saying the government is not doing enough, and I think they shot some people, like 2-3 people on the street, and really badly. So I was just looking in the news.
Can you see us now, George?
No, you're frozen at the point where we stopped.
Oh, we have to reconnect.
Wait a minute, πες το. Ας μας παίρνει.
Αυτό που είπατε, εγώ έχω την αίσθηση ότι το κατάλαβα, δεν ξέρω.
Ποιο αυτό εδώ, φυσικά το κατάλαβες αλίμονο, αλλά τώρα αυτοί ίσως να μην έχουν καλό background στα αυτά.
Ναι, στα φυσική, ναι, εγώ είμαι...
Τι να τους κάνω, εντάξει. Το θέμα είναι γρήγορα, δεν είναι, γι' αυτό και...
Δίκιο έχετε. Έτσι καλύτερα.
Hi, now I can see you again.
Έχουν πατημένο το mute αυτό.
Hello?
Can you see us?
Yes, I can see you. Can you hear me?
Yes.
Okay, good. Okay. So I heard while you're frozen on the screen, I heard you explaining the concepts. You did very well. So why don't you explain it there, and I'll be sitting by.
No, I understand quite well the first bipolar measurement, but then the second and the third are a bit unclear to me. How do they relate to the whole ECG, to the whole heart ECG?
Okay, it's no problem. You understand how the first one is done, right?
Yes. I understand. I don't know about the others.
Okay, no, let's, let's start with you and then we will go on to everybody. I mean, nobody's going to be left out. You understand how the first one is done. You have your right hand versus the left hand. You put a voltmeter and you watch it in time, correct?
Yes.
Okay. And I said that this represents the projection, if you want, of the heart vector on this side of the triangle, because this is indeed measured. And actually the distance of the triangle is nothing else but a scale, okay? The triangle is a fictitious thing. It's just something that we invent.
It doesn't exist. Yeah.
Okay?
But this is just a half vector? Why is it half?
What do you mean half?
You said half a vector? Or
What?
did I?
No, you didn't. Maybe it's my English. I didn't say half a vector. I said that there is a projection of the heart vector, not half the vector. Heart.
Oh, the heart. Okay.
Okay, and the vector that represents the heart, the electrical activity of the heart. It is the projection of that vector on this side of the triangle.
Okay.
Okay, now let's repeat the process by putting the electrode on the right hand and the left foot.
Yes.
Again, you're going to measure something, right?
Right.
Okay. That something is going to be a projection again of the same heart vector on this side of the triangle, which is called Latin 2.
Yeah.
And repeat the process. The same thing will happen on the other side.
Okay. And why is it 1 minus 2 plus 3 is 0?
Well, look at the geometry now. Just look at the projections. If you take the projections, they come exactly to that. This comes out of mathematics, out of trigonometry. But it is a very simple thing to remember. Okay, let me put you on the next slide. Okay, you see this slide here?
Yeah.
Okay. Down below, at the left-hand side of the picture, you see a torso wearing the 3 sets of electrodes.
Yeah.
Okay? Do you understand how this thing becomes now? What you measure in each one of those, right?
Yeah.
And in the middle you see 3 intersecting lines and a red vector. All right? Now, if you look at the bottom picture, the right-hand side on top, you see the triangle I've been talking to you about, and how this vector projects on all sides.
So the red is the summation of the 3 vectors?
That's right. It is the summation of all the small vectors in the heart and the summation of the 3 vectors according to the rule that I gave you. 1 minus 2 plus 3.
So every vector is placed on one of those 3 lines and then that's summed up to get the final? Is that what's happening?
Well, there are 2 ways you can look at it. Either you know what the vector of the heart is and you can predict what is going to be at your right hand, left hand and foot, or because you don't know what is happening in your heart, you measure what is happening between your right hand, left hand and left foot, and you infer from that the central vector.
But what you get is just one ECG, right, from the machine?
No, the vector is
Get
three.
three.
The vector is 3 ECGs from the machine. You have to take channel 1, which is the 2, channel 2, and channel 3. The only thing is that you need only 2 of those to infer, because the third one comes out of the other 2, always. Because of the rule that I told you. Anyway, let's leave this. I'm going to come back to it at some other point. Let's go. The only thing that you should keep from here, I'll find a way to hammer this thing in your head one way or the other, so don't worry about it. Let's go back to what we read between right hand and left hand, or right hand and left foot, or left hand and left foot. Okay, you see in this you see 3 little boxes that contain ECGs. Okay, do you see that? Okay, if we take the first, the Latin one, which is the one above the head of the guy here, and we go to above that, you'll see a representation of the ECG. Do you see it?
Yeah. Yeah.
The ECG has different deflections. It has a P deflection, it has a QRS complex, and a T deflection. Okay? Now, each one of those represents different parts of the heart being activated. Why? Because the vector that we said before is influenced by what part of the heart is activated at all times. Well, let me not get you onto this. I'll get back to this in a minute. This is what you see as a normal electrocardiogram. You see that this is, it has a little bar under the P complex, the P deflection, the P wave.
One second, George. We need to find the slide. Can she go out and try to find part 3?
No problem, I wait.
You see part 3? That's part 3, yeah. Okay, go ahead.
Okay. Now, what is this? This is the oscillation of one ECG in time. It is about 1 second long. Okay. You have a little bar that says 200 milliseconds. This allows you to decide about the total length, correct? You see the little bar that says 200 milliseconds on the left-hand side?
Yeah.
Okay.
Yeah.
This you have to learn by heart. You have to recognize all these events. What are the events? First is a P wave. The P wave represents the depolarization of the atria. Okay, which means it represents the time that the heart contracts in the atrial part to push the blood that has come into the atria from the superior and inferior vena cava on the right side, or from the lungs on the left side, to push them into the ventricles down below. Okay? Now, there is a so-called PR segment that you see it there noted at the bottom. You see it? Mm-hmm. Okay. The PR segment represents the time that it takes for the AV node to be transversed by the action potential. Remember I said that in the AV node there is substantial delay of the signal? Do you recall that? We said that this morning.
I don't think you said that.
You don't
Maybe
think so? Okay, hold on. I'll drive.
Maybe we didn't hear it.
I'll drive back. Okay. You see this? You recall this on this morning's?
Leave it there.
You recall this from this morning?
Yeah.
Remember that I said that it takes 70 milliseconds to arrive from SA to AV node?
Oh, this delay. Okay.
And then I said that it takes 116, it cannot be the His bundle, it's so slow, it is lost in the delay there. You recall that?
Yeah. But we know that's long, that's okay.
It sounds that long. Well, listen, if you're getting tired, we can stop at 4 o'clock and we can pick up next time. There is no problem. I'd rather have
I'm talking about the delay, not about the
No, but you see...
AV node delay.
No, that would be a good idea.
What?
That would be a good idea if it's...
I'd rather schedule an extra lecture rather than have you tired. It doesn't pay me to talk and,
Yeah, no, that would be a good idea actually, George.
Okay, well, let's go for 20 minutes and then we call the day. Okay?
Yeah.
Okay.
All right. At least let's go through this. So, this delay that we said that, you can actually measure it on a human being by measuring the PR segment.
You can measure the delay by measuring the PR segment. Is that what you said?
That's right.
The delay between, the conduction between the SA
It's hard to hear. There's like a fuzzy.
Okay? Because what does PR say, the PR segment say? It says how long it takes from the end of the depolarization of the atria before the ventricles are depolarized. So all this time is going to be spent in one and one place only. This is the AV node. Okay? Now, the QRS complex is a very interesting one. It is the depolarization of the whole muscle, 90%, I shouldn't say the whole muscle of the ventricles, but 90% of the total muscle mass of the heart. And it is a very sharp deflection, and at that time it goes positive, negative, and it returns to zero. Why? Because at zero the whole heart is depolarized, so no matter what you measure, it is between your electrodes, it is going to have this, all your electrodes see the heart as depolarized, therefore no currents are going to flow. Remember when I was telling you about vectors before, that if you are symmetrical between the electrodes, you are not going to see anything? Well, now when the whole heart is depolarized, it is like the same thing is in the middle of the two electrodes. There is no one part of the heart that's different than the other, because the wave has covered everything. So it is returning between S and T into the time that the ventricles contract and empty. And this is what the ST segment represents. It represents the contraction of the ventricles and the emptying of them. And then we have another wave that follows this, and this is the T wave. The T wave is nothing else than the wave of the ventricular repolarization. This is when the ventricles start repolarizing, start becoming back to normal. I mean, not to normal, to rest, I should say. Everything is normal, hopefully. You like that? Okay? And now, before the next P wave arrives, we have a long period of silence. This is the time during which the ventricles are relaxing and, of course, filling with blood. Now, why should that be flat? It should be flat because there is no activity in the cells at all. They are relaxed. Remember? No activity means that the whole surface of the heart has the same voltage, no matter where you are. And therefore, in your electrodes is not going to be any different, whether you look at it from one side or from the other. I'm listening.
Yes.
Okay. Is this at least understood?
Yes.
Yes.
Okay. Now what you have here is a description of what a QRS is. Just in case, can any one of you, from what we said up to now, tell me the height at any particular point? Let's take the T wave, okay? And let's take the height at the peak of the T wave. The height meaning from the flat line that runs between P and Q, or between S and T, or between T and P. This is the zero line, so to speak. Can you tell me what the height of T means?
What is the question?
The height of the T wave, let me draw it for you for a second. Remember when we said here, this part, this height, what does it represent?
Is it like potassium channels open? Or potassium?
Don't get lost. You are not looking at one cell now. You are talking to a few millions of cells.
Ventricular repolarization.
This represents ventricular repolarization, correct. But in terms of what we were talking about, the vectors, can anybody think of what it represents?
Vectors. In terms of
Vector-
vectors,
vector?
what does it represent?
Okay, listen. I'm going to write this up. You're going to give me 3 days. I'm going to write it, or 4 days. I'm going to write it up and send you this vector thing, or find a good chapter somewhere that explains it. Because if you don't understand it here, you're not going to understand it from the book. Okay? I'm going to find some material to send you, and I think this will take care of it for you. And if not, then I'm going to write it myself. But I think I understand how I have to teach it to you. I have to first find a few basic physics to pass on to you, just for quick reading, not for learning, for Christ's sake. Eh? Okay?
Okay.
Now, well, from here on, let's stop for a minute on this slide, because I'm not going to waste your time. You know, I see you are tired. But what you have here, can you see it on your?
Yeah, you have it.
All right. I think that you asked me a little bit before what its part of the ECG represents. All right. Okay. Here you have the different phases of the heart activation. You have, in fact, a whole series of activation of the heart, and down below you see you have an ECG, which is in development. Okay? So, by red it shows you what parts of the heart are active, and down below how the deflection of the ECG is going to be. You see it? Let's take in the beginning. It says P wave. You see the two atria active by red color. They are shown with red color here. Okay? And you have a deflection that's going up in red down below. You see right below the schematic of the atria and the ventricles, you see the trace, the ECG trace. You see it?
Yes.
Where it says conducting system of the heart, down below from there, under the word conducting. Do you see it?
No.
No? Or yes?
No. Oh, conducting? Just.
The word, it says A, conducting system of the heart. You see it there?
Yes.
Down below from the word conducting is a small square. It has,
Yeah, we see that.
you see, down below it has a trace that just starts deflecting. You see this? With red.
Yeah.
Okay.
Yeah.
This part of the P wave